Hello, am I audible? Hello, hello, am I audible? Can anyone confirm? And is my screen visible? Okay, thank you. So good afternoon, everyone. Welcome to this NPTEL live session for the NPTEL course Introduction to Machine Learning. My name is Ayan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So this is the week 8 live session. So in this live session, I will discuss some practice problems on Bayesian network and naive Bayes, and also on some problems on uh, boosting, gradient boosting, and also from this week's content which are undirected graphical models. So on these topics, Bayesian, mainly on Bayesian network and naive Bayes and boosting. So these are the topics that I will cover. I will cover practice problems for these topics, and after that I will also try to answer your questions and doubts if you have any. So we can start the problem solving part of this session. So this is the question 1. So you can see a Bayesian network given here, we're consisting of 9 nodes and or 9 variables here, and each variable is a binary variable, that is it can take 0 or 1 values. So you have to find the answer for this question: which of the following is or are true for the above Bayesian network? So for this Bayesian network, there are 4 options given. So basically you have to find out the conditional dependencies between different pairs of vertices. So 4 options given, which of these following is or are always true for the above Bayesian network? You can write your answers in the chat. Such questions on Bayesian networks can be a little tricky, but if you know the exact rules for the d-separations, then you will be able to answer this question. Has anyone found any answers for this? Vijaya says C, which is probability of BH given EG equals probability of B given EG, probability of H given EG. Okay, so any other answers? Anyone else? So in this question, for the first option, you have to find out whether A and B are independent or not given G. So this is what this probability expression tells about. So P of A B given G equals P of A given G, P of B given G. That basically means you have to find out whether A and B are conditionally independent or not given G. In the second option, it is probability of AI equals probability of A into probability of I. That means whether A and I are independent or not without any evidence. So no evidences are there. So you just have to find out whether A and I are independent or not. In third option, it says whether B, A and H are conditionally independent or not given E and G. So E and G, these are the two evidences given, and based on that we have to find out whether B and H are independent or not. And in the fourth option, it is probability of C given BF equals probability of C given F. That means whether C is conditionally independent of B or not if F is given. So all these four options are basically based on conditional dependency. So you have to find out the such conditional dependency relationships from this Bayesian network given in this figure. So first option is probability of AB given G equals probability of A given G, probability of B given G. So here is the variable A, here is the variable B. So you have to, and this G is given. So this G is given. So you have to find out if A and B are conditionally dependent or not, conditionally independent or not given G. So for that you have to find out. So in the there are three separation rules. Let me write those rules. First rule is that let's consider this IJK three networks, three nodes. Oh, sorry. Yeah. IJK three nodes. So if the arrows are in this way, in that case I and K are conditionally independent given G. So G given J. So J is the middle node, and if J is given, I and K are independent, conditionally independent. Second rule is I J K. So the two arrows are in two different directions, and I J K are the three variables, and J, if J is given, still I and K are conditionally independent. This is rule 2. And the third rule is, so here the direction of the arrows would change. So both the arrows would be directing towards J. So now in this case, if J is given, then I and K are not conditionally independent. So in these cases, these are conditionally independent. So yes, in this case I and K are not conditionally independent if J is known. So J or any of the descendants of J must be unknown, so that I and K are conditionally dependent. So these are the three rules. So it might be a little complicated at first to understand, but if you go through the video lectures once again for this course, and you will be able to understand these are the three rules that we have to follow. So for the first option, whether A and B are conditionally independent or not given G, so here we can see that there is one path from A to G, and here from B to G, this is another path, and G is given. So that means it falls under the third criteria. You can see that there is one path from A to G, and there is one path from B to G. So this falls under the third criteria of the separation rule. and j is given. So if g is given, then these two variables are not conditionally independent. So first option is not right, so option A is not right in this case. So if g was not given, then it would have been conditionally independent. Second option, which is option B, says whether A and I are conditionally independent or not. So from this diagram you can see this is A and this is I. So no other variables are given, so no, there is no evidence. We just have to find out the dependency between A and I, and you can see that I is dependent on B, like this. I is dependent on B, but A cannot influence I in any way. So path for A reaches up to G, but after that we don't have any path from here to I. So A cannot influence I. I lost the internet connection for a while. Is my screen visible again? Is my screen visible? Can anyone tell me in the chat? Okay. So we were inspecting option B. So option B is correct here, because A cannot influence I in any way. So A and I are independent. From this graph we can see that I is dependent on B, but A cannot influence I, because there is no directed path from A to I. So A and I are independent of each other. So option B is right, and option C says whether B and H are independent or not given E and G. Yes. So B is here and H is here, and these are the two evidences given, E and G. So here we have to find out all the paths from B to H. So we have to find out all the paths from B to H, and we have to check whether all the paths are blocked by these two evidences or not. So one path is from B to H is this path, and this is blocked by E. E is the evidence given, so it is blocked by E. And another path is this one, like this way, from B, C, D, G, F, H. So this is another path, and G is the evidence that is given, so it falls under the third rule again. Here falls under the third rule, and if G is given, this path is not blocked, so we can reach from B to B to H through G. So all the paths are not blocked from B to H. That means B and H are not independent, conditionally independent given E and G. So this is also not right. And final option is D, which is probability of C given BF equals C given F. That means whether B and C are conditionally independent or not. and we can easily see that B is influencing C because there is a direct link between B and C. So these two variables cannot be conditionally independent. B directly influences C through this edge. So D is also not right. So only correct answer is B. So B, probability of AI equals probability of A into probability of I. This is the only correct answer. Other three options are wrong. So this is how you have to check the conditional independency between any pair of vertices given some evidence or given some variables. You have to use these three deseparation rules, and you have to find out whether all the paths between a given pair of nodes is all are blocked or not. If all the paths are blocked, then they are conditionally independent, otherwise it's not. So this is how you have to do. This is so option B is the correct answer here. So these problems can be a little tough, but you have to practice some more examples on this so that you understand the overall concept of conditional independency and the deseparation rules. Question 2, this is again on Bayesian network and conditional dependency. So in this Bayesian network given, you have to find out which of these four options are correct. Option A says D is independent of B when C is known. Option B says A is independent of C when E is known. C says A is independent of B when E is known, and option D is A is independent of B when C is known. So these are the four options, and you have to find out which of these options are correct. So multiple options may be correct here. So this is a much simpler graph than the previous one, much smaller as well, so it would be easier to apply those deseparation rules on this smaller graph. Vijay says B, which is A is independent of C when E is known. See, this is A, this is C, and E is known. Any other answers? There might be multiple options correct in this question. Vijay has written A, which is D is independent of B when C is known. So this is D, this is B when C is known, this one. Okay. So in this question, first analyze option A, which is D and B when C is known. So this is the this falls under the second criteria that we discussed in the previous question. This criteria that I, J, K, these are the three variables, and one edge goes from J to I, another edge goes from J to K. So this is that case that there are two descendants of C, D and B, and if C is known, then D and B are independent of each other. So option A is correct here. First option is correct. Now option B, which is A and C are independent of each other given E. So this falls under the third criteria of the deseparation rule, which is I, J and K, and there might be some descendant of J dash as well. So in this third criteria, it says that this should be like this, yeah. So both the arrows would be directing towards J, and J dash, this J dash is some descendant of J. So if J or any descendant of J, which is in this case J dash, is known, then I and K are not independent of each other. So this is the rule here in the third criteria. So in this case we can see that there is an edge from A to B, there is an edge from C to D, and E is one descendant of this D. So this structure is very similar to this one, isn't it? This whole structure. So E is the descendant J dash, and D is this J, and I and K are A and C respectively. So if this D or E is known, then A and C cannot be conditionally independent. So option B cannot be right. Then option C says A is independent of B when E is known. So A is independent of B when E is known. So again we can use the same criteria here. The third criteria of deseparation rule we can use, and we can say that A and B cannot be conditionally independent of each other if E is known, because E is a descendant of D. Again, D has this structure of like the third criteria as we have seen. So option C is also not right using the similar criteria, and option D is A and B is known, B is independent when C is known. So this would be right, because we have this path from A to C, and but this path from A to B is blocked by C, because this C is known, so this path is blocked by C, and if all the paths between A and B are blocked by one or more evidences given, then the pair of variables are conditionally independent of each other. So option D is also right. So A and D, these are the two options that would be right in this case. So again, just like the previous question, you have to find out which criteria you have to use for the deseparation rule, and you have to find out that way you have to find out whether all the paths from the from one vertex to the other is blocked by any of the evidences or not, given using those three criteria of the separation rules. And using those rules we can see that A and D are the correct options, B and C are incorrect. So this was question 2. A and D would be the correct options here.
Can you explain D again?
D, okay, so D, option D says that A and B given C. So in this case, this is the path from A to B, and a path is blocked by a variable if it falls under the those two criterias, the first two criterias that we have. So I, J, K, or I, J, K. So these are the first two criterias. We can see that C, one edge goes from C to D, another edge goes from C to B. So that means it is this case, the second case. See, two arrows are in two different directions. So that means J is blocking the path from I to K, and if J is given, I and K are conditionally independent. So C is blocking this path from A to B because C is given and it falls under this second criteria. So C is blocking the path from A to B, and this is the only path to go from A to B. So all the paths from A to B are blocked by one or more evidences, in this case only C. So if all the paths are blocked, then the pair of variables are conditionally independent of each other. A and B are conditionally independent of each other given the evidence C. So you have to.
C is known, I think. So
Yes, if
blocking.
so in the second criteria, I, J, K. So if J is known, then J is blocking the path between I and K, and we want the path to be blocked between I and K if we want them to be conditionally independent of each other. If all the paths are blocked, then we say that they are conditionally independent of each other. So we need block. If all the paths are blocked, then only they are conditionally independent of each other.
Okay.
So if we find at least one path that is not blocked, then we can say that they are not conditionally independent. We need all the paths to be blocked for them to be conditionally independent. And here in this case, C is blocking that path using this criteria. So this is how you have to analyze all the four options, and you have to see which of these is or are correct. So in this case, A and D are the correct options. So let's move on to the third question. So this is on a Bayesian network, and so you have to calculate these probability values basically. So three variables are there: rain, sprinkler, and wet grass. These are the three variables given, and some probability values are also written down here. Probability of R means rain, S means sprinkler, W means wet grass. And all these three variables are binary variables. It takes each variable takes either 0 or 1, and these probability values are given, and you have to find out this probability of S given W and R. So you have to use Bayes theorem or some other methods from Bayesian network to calculate this probability value. And this is a much easier question than finding out those conditional dependencies. Here you just have to use Bayes theorem. and this sign, this one, this is negation sign, this one, like this is negation of that variable, or basically complement of that variable. So has any one of you calculated this probability of S given W and R? So in this question you have to find out this S given W and R. So for, you have to use Bayes theorem for this, because you don't have this probability value in this the probability values that are given here. So if you use Bayes theorem, so let me write down the actual form of the Bayes theorem. Probability of A given B equals probability of B given A, probability of A divided by probability of B given A, probability of A plus probability of B given A bar, probability of A bar. So this is the Bayes theorem. So if we apply this Bayes theorem to find out this probability, it would be probability of W given S comma R into probability of S given R divided by probability of W given S comma R, probability of S given R plus probability of W given S bar comma R, probability of S bar given R. And now this probability of S W given S and R, this is given here, this probability is given, and probability of this one, probability of S given R, is this is nothing but probability of S, because we can see that S and R are two conditionally independent variables. They don't depend on each other, so probability of S given R is just probability of S, and similarly probability of S bar given R is probability of S bar, and this probability of S is given here. So you can also find out probability of S bar from this. If it is 0.8, probability of S bar 0.2, probability of S bar will be 1 minus 0.2, which is 0.8. And another probability value, probability of W given S bar comma R, it is given here. So all the probability values that you need for this Bayes theorem you already have in this given table. So you just have to plug these values into this formula and you will be able to find out the answer. So the correct answer would be C, 0.22, and the detailed solution I have also written. This is a different form of the same Bayes theorem, but the actual calculation would be exactly same. So this way you have to analyze this Bayesian network for these three variables, rain, splinter and wet grass, and based on those probability values that are given here, you have to apply Bayes theorem and you have to compute this probability value. So this is how you have to calculate this, and after we apply the Bayes theorem, all the probability values we can already find out from this table, that of all the probability values that are given here. So here correct answer would be option C, 0.22. So now let's move on to question 4. Is there any questions or doubts on this question, third question? So now question 4, what is the naive assumption in a naive Bayes classifier? So which assumption is naive, which is why we call it naive Bayes. So there are 4 options. Option A is all the classes are independent of each other. Option B, all the features of a class are independent of each other. Option C, the most probable feature for a class is the most important feature to be considered for the classification. Option D is all the features of a class are conditionally dependent on each other. So which option is the naive assumption in a naive Bayes classifier? You can write your answers in the chat. Akanksha Joshi says B, which is all the features of a class are independent of each other. Okay, so any other answers? Anyone else? Vijay also says B. So here the correct answer would be B. So 2 of you have written the correct answer in the chat. All the features of a class are independent of each other. That is the naive assumption in naive Bayes. So if we have x1, x2, x3, 3 features, and C is one class, then x1 comma x2 comma x3 given C. So this probability would simply be probability of x1 given C, probability of x2 given C, probability of x3 given C. So these three features x1, x2, x3 are independent of each other given the class. So for a class, these three features are independent. So that's why option B would be the right answer. This is the naive assumption in a naive Bayes classifier.
So,
So option B, this is the right answer. So let's move on to question 5. So a spam filtering system has probability of 0.95 to correctly classify a mail as spam, and 0.10 probability of giving false positive. So that means it is if the mail is not spam, but it still classifies it as spam, so that is false positive. So the probability for that is 0.10, and it is estimated that 1% of the mails are actual spam mails. So suppose that the system is now given a new mail to be classified as spam or not spam. What is the probability that the mail will be classified as spam by the system? So 4 options are given. So again you have to use the probability related formulas like Bayes theorem or some other theorem. So here we need to consider two random variables to solve this problem. S is one random variable which denotes system classifies a mail as spam. So this is one random variable, and aim is another random variable that we will consider, which is a mail is actually spam. So if system classifies a mail as spam, that doesn't mean it is actually spam. It can also be a non-spam, but it might be a case of false positive. So that's why we consider two random variables, s and m. So now we have to find out what is the probability of the mail that will be classified, that the mail will be classified as spam. That basically means we have to find out probability of s. This is what we have to find out, and the information that are given to us is a probability of 0.95 to correctly classify a mail as spam. So this is the probability for correctly classifying a mail as spam. That means this probability is probability of s given m. So the mail is actually spam, and it is classified as spam by the system. So this 0.95 is the probability of s given m, and this false positive is just the opposite of that, s given m bar. That is, it is not spam, but it is classified as spam by the system. And this 1%, so this 1% is just the probability of spam mails, which is probability of m. So this we have to find out probability of s. We will use Bayes theorem here. Probability of s given m into probability of m plus probability of s given m bar into probability of m bar. And we have already found out all the probability values that we require. Probability of s given m, this is 0.95. Probability of m is 0.01, which is 1% given in the question. S given m bar, which is the probability of false positives, which is 0.10, and probability of m bar, which is 1 minus probability of m, which is 0.99. So you have to just calculate these, you have to put these values into this formula, and you have to calculate the probability of s here. And if you calculate this, it would come option C, 0.1085. So this is how you have to solve this. You have to consider two random variables, s and m. S denotes it is classified as spam, and m denotes it is actually spam. And now using these two random variables, you can define all the probability values that are given in this question. Three probability values are already given, 0.95, 0.10 and 0.01, and then you have to compute probability of s given those probability values. So this is how you have to compute, and this is the detailed solution I have written. It is same as how I discussed it in the last slide. Is there any questions or doubts in this question? Okay, so we can move on to question 6. So as very small Bayesian network is given, just two nodes are there, f and c, and an arrow goes from f to c, and three probability values are given. One is probability of f is 0.1, probability of c given f is 0.8, probability of c given f bar is 0.3, and you have to find out these two probabilities, probability of c and probability of f given c. So these two probability values you have to find out based on this Bayesian network, and these three probability values. first probability value that you have to find out is probability of C. So probability of C you can find out using this conditional probabilities. Probability of C given F into probability of F plus probability of C given F bar into probability of F bar. And all these probability values are already given here. So probability of C given F is 0.8 and probability of F is 0.1. Probability of C given F bar is given as 0.03 and probability of F bar is 1 minus probability of F, which is 0.9. So if you compute this, it will be 0.08 plus 0.27, so it will be 0.35. And now similarly probability of F given C you have to find out this one. So it would be using Bayes theorem, C given F into probability of F divided by probability of C, and probability of C you have already computed, and probability of C given F you already know from this diagram, which is 0.8, and probability of F is 0.1. So you can plug these values into it and it will come out to be 0.23. So option A would be the correct answer. 0.35 is the probability value for C, and 0.23 which is the value for probability of F given 3. So these are the two correct answers here, and this is the calculation process that I have already shown in the previous slide. Option A is the correct answer. So does anyone have any doubts or questions? Now question 7, this is on boosting, specifically on AdaBoost. So in AdaBoost we give more weights to the points having misclassified in the previous iterations. So this is how actually AdaBoost works. Now if we introduce a limit or cap on the weight that any point can take, for example say we introduce a restriction that prevents any point's weight from exceeding a value of 10. So we introduce a limit or cap on the weight that any point can take. So which among the following would be an effect of such modifications? So three options are given. So it will make the final classifier robust to outliers. Option B is it may result in lower overall performance. Option C is none of these. So what would happen if we introduce a limit or cap on the weight for each of the points? So it cannot exceed a given value. In this case, let's say 10. So what will happen? What will be the effect of that on the performance of the AdaBoost? And multiple options may be correct in this question. Akanksha Joshi has written B, which is it may result in lower overall performance. Okay, and any other answers? So option B is obviously correct, that it may result in lower overall performance, because we are modifying the algorithm in such a way that we are limiting the weight on any point. But option A is also correct here. It makes the final classifier robust to outliers. So what happens when there are outlier points? So it would those points are generally misclassified. That's why those are outlier points or noisy points. So and the error values on such outlier points are much higher. So weights on those points would be much higher, and if we can limit the weights on such outlier points, it reduces the importance of those outlier points, and we want to ignore such outlier points, because outlier points might be hampering the performance of the classifier. So we want those outlier points to be ignored. So if we put a limit on the weight that those outlier points can take, it makes the classifier robust to such outliers. So option A is also correct. So there are two correct options here. So it makes the final classifier robust to outliers, and it may result in lower overall performance. It will certainly lower the overall performance, because not just the outlier points but also the normal points in the datasets are also affected by this modification. So we are limiting the weight for every point in the dataset. So other points might also be affected, and that's why the overall performance might also degrade because of this modification. So both the options would be correct here, A and B. So this is a good method to make the classifier robust to the outliers. So these are the two options correct, and this is the detailed solution I have written. So it basically outliers tend to get misclassified. As the number of iterations increase, the weight corresponding to the outlier points can become very large, resulting in subsequent classifier models trying to classify the outlier points correctly. But we don't want that. Outlier points, we don't really want to classify those are noisy points. So this generally has an adverse effect on the overall classifier. So restricting the weights in one of those is one of the ways of mitigating this problem. However, this can also lower the performance of the classifier. So this is the detailed answer for this question. Question 8. Which of the following algorithms are not an ensemble learning algorithm? Multiple options may be correct here. Random forest, AdaBoost, gradient boosting, decision trees. So which of these following algorithms are not ensemble learning algorithms? Akanksha Joshi has written D, which is decision trees. Okay. So which of the following algorithms are not ensemble learning algorithms? So option D is the only correct answer, decision trees. Random forest we know is a ensemble learning algorithms. It is an ensemble of decision trees only. So an AdaBoost is also an ensemble learning algorithm. It is a boosting algorithm which trains multiple classifiers and combines the result of multiple classifiers iteratively to find the final classifier. And gradient boosting is also a boosting algorithm, so it is also an ensemble learning algorithm. So only correct answer here is decision trees. So decision trees are not ensemble learning algorithms. Option D, this is the correct answer. Question 9. This is from the undirected graphical models. So you are given this undirected graphical model, and in this undirected graphical model below, which nodes are conditionally independent of each other given B? and multiple options may be correct here, so select all that apply. So in the undirected graph given below, which nodes are conditionally independent of each other given B? And this is not a Bayesian network where we have these directed edges. Here we don't have directed edges, that's why it's called undirected graphical model. And the node B is given, this node is given. Now which of these following pairs are conditionally independent of each other? So for such questions on undirected graphical models, what you have to do is that you have to find out for a given pair of nodes, you have to find out whether that goes through B or not. You just have to find out that. So first option is A and D. So here is A and here is D. So we have to find out all the paths that go from A to D and whether all the paths are blocked by B or not. If all the paths are blocked by B, then A and D are conditionally independent of each other given B. But we can see that there is one undirected path from A to D which does not go through B. That means B cannot block that path. So that means A and D are not conditionally independent of each other. So first option is not correct. Then D and D. Here is D and here is E, and there is a direct path from D to E. So that means this path is certainly not blocked by B. That means D and E are not conditionally independent of B. So we need all the paths to be blocked by B in order to make them conditionally independent. And then C and D. So C here and D, and we can see there is one path from C to D like this, undirected path. So that means this path is certainly not blocked by B. So this pair is also not conditionally independent. Now A and F. This is A and this is F, and there is a direct path from A to F. And this path is also not blocked by B. So that means it is also not conditionally independent. So the answer would be E, none of the above. So you have to find out if all the paths between that pair of vertices is blocked by the evidence. In this case, evidence is just B, evidence on whether all the paths are blocked by B or not. So here we can see that for any of the options it is not correct. So option E would be the correct answer, that none of the above. So for every pair that is given here, they are not conditionally independent. So all pairs have alternate routes to reach each other, and that doesn't pass through B. So option E would be the correct answer. So for undirected graphs, you just have to find out all the paths from one node to the other, and whether it is blocked by the variable that is given or not. In this case B is given, So in other cases some other variables might be given, so you have to find out whether the variable which is given is blocking all the paths or not, and if it is blocking all the paths, that means the two variables are conditionally independent of each other. Question 10, and this is on naive Bayes. So consider the following data of 20 budget phones, 30 mid-range phones and 20 high-end phones, and this table is given that for budget phones, out of the 20 budget phones that that are there, so 15 have single SIM, 5 have 5G compatibilities, and 0 has NFC, and total 20. So similarly for mid-range phones these three features are given, for high-end phones also these three features are given, and total 20 here. So now consider a phone with 2 SIM card slots, that means not single SIM, and 2 SIM card slots and NFC but no 5G compatibility. So these are the three features of the phone you are given. So calculate the probabilities of this phone being a budget phone, a mid-range phone and a high-end phone using the naive Bayes method, and the correct ordering of the phone type from the highest to lowest probability. So this is you have to find out. So there are three features for each phone. Let's call the first feature single SIM as SSIM, SIM, single SIM. Second one is 5G. Third one is NFC. These are the three features of a phone, and the phone that you are given is this one. So two SIM card slots, NFC but no 5G compatibility. That means you have to find out these three probability values. Probability of being a budget phone given negation of single SIM because it has 2 SIM card slots, NFC, or you should write 5 no 5G, so negation of 5G and NFC. Similarly you have to find out probability of being a mid-range phone given negation of single SIM, negation of 5G and NFC, and probability of high-end phone given negation of single C, negation of 5G and NFC. So these are the three probability values that you have to find out from this table that is given here, and you have to use naive Bayes theorem. That means every feature is independent of the other features given a class. So for this question, this is as it is on naive Bayes, so you have to use this formulation. So probability of class given x1, x2, x3, these are the three features, and class, this class variable can take three values here: budget, mid range, or high end. So these are the three possible values for this class. And x1, x2, x3, these are these features: single sim, 5G, and NFC. These are the three features. So these are x1, x2, x3. So probability of a class given x1, x2, x3 equals probability of the class into probability of the class into probability of x1 given class into probability of x2 given class into probability of x3 given class. Because you are using naive Bayes, so you have to use the naive Bayes assumption here, that all the each feature is independent of the other features given the class. So you have to find out this probability value for different classes: budget, mid-range, high-end, using this formula. This is the formula that you have to use. And now for the budget phone, so this is the first probability of budget given negation of single SIM, negation of 5G, and NFC. So for this you have to first find out probability of budget. So probability of budget is 20/70. Then probability of negation of single SIM given budget, which is 5/20, because there are 15 phones of single SIM which are budget phones out of 20. So that means there are 5 phones which are not single SIM in budget class. So that's why 5/20 is the probability. Similarly, you have to find out this probability of negation of 5G given budget and probability of NFC given budget, and this you have to calculate for all three classes, probability for budget, mid-range, and high-end. So you have to find out these three probabilities using the same formula that is given in the first line. So using this formula you have to find out these three probability values using the naive Bayes assumption, and if you compute these three probabilities, you will find out that mid-range has the highest probability, then high-end, then budget. So this is the answer, option C, mid-range, high-end, budget. This is the correct order of the probabilities from highest to lowest. So this is how you have to use naive Bayes to calculate all the probability values, and based on that you have to find out the correct ordering. So option C is the correct answer. Is there any questions or doubts on this question? So question 11, this is the last question. So Bayesian network is given here, consisting of 7 variables: d1, d2, d3, and s1, s2, s3, s4. You have to find out the joint probability distribution for all the variables in this given network. So joint probability distribution basically means probability of all the variables d1, d2, d3, s1, s2, s3. So this is the joint distribution, and what would be this probability value given this network. So from this network we can find out the relationships between every pair of nodes, and based on that what would be the correct answer here for the joint probability distribution. Akanksha Joshi has written A. Okay. Any other answers? So for joint probability distribution, what you have to observe from the network is how the variables are related to each other. So d1, d2, d3, these three variables are not dependent on any other variables. So these three variables are independent of any other variables. So you for these three variables, it would be probability of d1, probability of d2, probability of d3. These are not dependent on any other variables. Now S1, so S1 is dependent on D1 only, so there is only one incoming edge for S1. So S1 is dependent on D1, so probability of S1 given D1. Now S2, for node S2, it is dependent on two variables, D1 and D2. So that means it will be probability of S2 given D1 and D2. So this is D1, probability of S2 given D1 and D2. And now S3, so S3 is also dependent on two variables, D1 and D3. So it would be written as probability of S3 given D1 and D3. Now finally S4, which is only dependent on D3. So it would be probability of S3 given D3. So from the first option, we can see that option A is the correct answer. So you have to analyze the graph and find out which variables are not dependent on any other variables, and you just have to write those probability of those variables first, and then you have to find out for each variable which are the variables it is dependent on. Like S1 is dependent on D1 only, S2 is dependent on D1 and D2, S3 is on D1 and D3, and S4 is on D3. So this way you have to find out this expression. So option A is the right answer. A is the right answer here. Yes. So this is the end of the problem solving session. So if you have any questions or doubts regarding any of the questions that I discussed today, you can ask, or if you have any other doubts and questions regarding any part of this course, you can also ask. So if there are no questions or doubts, so we will end this session. Thank you everyone. Thank you everyone. I'm ending the session now.